This paper is the continuity of the first one I presented this afternoon. And the idea here is to sometimes, in practical way, what we expected from the welding is that, is it qualified or not qualified? That's the final reason to have a weld bid. Is its qualification under welding procedure or for the welder, for the performance qualification? But sometimes people, normally they say, okay, this is a good weld, it's not so good. We try to correlate some visual aspect with the welding parameters. Let's say, okay, this is a beautiful weld or is not a beautiful weld. Let's say, hopefully, what's that try to do for stainless steel, okay? Again, we come out with stability and regularity, as we spoke earlier. Let's say to try to define stability is when welded joint with metal, regularity and homogeneous in the whole bead generate a minimal sputtering, geometrically homogeneous pull in all bead extension. So basically, we try to reach a stable process by regularity method transfer. But if you allow me, I'll go faster because I talked all this afternoon about that. But again, what we're trying to reach is a stable short circuit period of time and also the open arc period of time. So by means of measuring the electrical signals, voltage and current, and we try to say, okay, by measuring that, we reach a nice visual aspect of the weld bead or not. That's the basic idea of this paper now. So we try to reach a low variation of short circuit and open arc duration, open arc period. That's our idea, to reach a uniform weld bead aspect. So let's see if we can come out with a good weld bead. Okay. So this work proposed to evaluate by use digital image processing, that the tools that we have for visual aspect, to evaluate the regularity of superficial aspect of the weld bead. When we do that by conventional gas metal arc weld operating with short circuit metal transfer, in this case for austenitic and duplex stainless steel wires. We try to also measure and correlate the superficial aspect with electrical signals from the process. Okay. As written in the previous slide, we try to do that by image processing. So basically what we have is, we take a picture, we develop just ordinary software with digital imaging image process. How that work? How does it work? We take a picture of the weld bead, seeing the face of the weld over the top, and a side of the weld. So basically here we see the weld bead and the cathodic region. Oh, sorry, the anodic region. No, the cathodic region. The cathodic region. Don't forget the basics of what. The cathodic region around the weld bead. And here just a scale to know each line is 1 millimeter apart from the other. So we take a picture over the weld and aside the weld. Here we have the weld reinforcement. Here we see the plate, and here the weld reinforcement. So we take two pictures, and our software analyze that. The nice thing or the trick that we came out here is we take the picture and we analyze let's say the bead width in this case. We measure the bead width. After we take the picture, we process the image and we analyze every movement or every variation of the width as an electrical signal. That's let's say the nice tricky of this analysis. The same here for the reinforcement. We treat the reinforcement, all the up and down, we analyze that as a signal. Which means that we have two signals here for the width, one here and the other here. and another signal to analyze on the reinforcement, following the profile of the reinforcement. So we analyze 3 signals. So we take a fast Fourier transformer, we analyze the standard deviation of the up and down of the bid width and the bid reinforcement. So we analyze a signal that make our life much easier than analyze that as it would be really an image. We just use the image to get a signal, and that signal, excuse me, and that signal represents the variations that we have in the bid width and the bid reinforcement. Okay, and again we correlate that with the standard deviation of the short circuit time and standard deviation of open arc time. And again, we, in the limit of a such frequency, that we consider that above that, below that frequency, we have a globular metal transfer. The same presentation again, sorry. So we came out with a maximum voltage, that above that limit we have a globular metal transfer, and the minimum voltage, otherwise you have a too drastic, let's say that, short circuit. As we showed in the first presentation, frequency too low, we have a big droplet. Frequency too high, we cannot have a proper metal transfer because we have 2 small droplets and the wire keeps hitting the weld pool. So we try to reach a suitable frequency. So we try to correlate that metal transfer with a nice bid profile. That's the goal of this presentation. Okay. So again, the lower the deviation of the arc voltage with time, the lower the index. So we can set up a suitable voltage for carry on the experiment and carry on the weld bit. Okay, this was done with 2 wire feed speed, 2.8 meters per minute and 3.8 meters per minute, two shielding gases, argon 2% of CO2 and argon 2% of O2. Materials, filler wires, standard austenitic 1, 308 and 229 for duplex wire. For base material again, the pretty standard materials, 304 for austenitic and 2205 for duplex base material. Okay. Here are all the tables. Again, if you're interested, you can find all the data on the paper. So please be my guest to look at. Here is just to show the amount of tests that we run. So sometimes like 69 tests just for this paper, because we need to find the current, we need to redo, we need to retest. So it demands a lot of experimental effort. That's the downside of work with process. We have to do a lot of experimental work. But here is the frequency, just to give you an idea. It goes from 9 Hertz to 44 Hertz. So below that level, we say that we go into globular metal transfer. Okay, the results. So for this regularity index, again, the lower the better. We try to reach. As we saw in the previous paper in this afternoon, for this just for all the data for the austenitic 1, 308 wire. So basically, we see a constant trend. We don't see too much variation over the voltage range, both for regularity index. We see here for 2.8 CO2, 0.8 meters per minute. Here is O2, and the one down side is the 3.8 meters per minute. So we see a constant over the range. There's no much variation. Perhaps we see some minimum values. Here we can see perhaps here some minimum. But the idea is that for austenitic wire, we have a very, let's say, good weldability. Over the voltage range, we can reach sound welding independent of the specific voltage. but in all the voltage range, we reach good values, let's say. But for the duplex, we can see some deep valleys here, so we may select voltage range here. Here is too high voltage, we have a cutting frequency here, so basically you have the three values. Here we have a valley here, so we say, okay, for welding in such condition, we end up with 17 volts, and here clearly another very small value, so where we should weld. Again, for the duplex stainless steel, we really have a more characteristic feature of having low index values, so where we should carry out our welding. Okay, here's the images of just a set of images. So we see the top view of the beads. Here in this case, just to present the paper, we select 9 to show you. And we try to characterize that first. We take the image and we select 6 welding engineers. So we have there, as they are qualified by the IIW, so they are international weld engineers. Okay, I must agree that an inspector would be best in this case, but we have the weld engineers. So we gave those beads to them and say, okay, please score that beads and say which one you think that is best, which one you think that's not so good, based on the border aspect of the weld bead, surface aspect of the weld bead, and overall aspect of the weld bead. So we say, okay, people look and say, that's a good weld, that's a sound weld, basically on just a superficial aspect, right? We're not trying to characterize penetration, things like that here. And try to say, okay, when someone says that's a good weld, how can a machine or a vision, a computer follows that trend and say that the weld is good. So here we try to evaluate the software we develop. It's simple software, really simple digital image processing. But in this case, the higher the grade, or the higher the score the weld engineer gave to the bead, the better, right? So we see that in black is the index that the welding, okay, that the software reach, and in red, in black, the grade that the software provided, in red the grade that the weld engineers gave to the weld bead. So we see a trend based on the deviation of the bead width and the deviation of the weld reinforcement measured like that signal I told you. So they try to follow the same trend. Okay, you have some difference, but when you see, okay, they both software and both weld engineers said that's the, let's say, most beautiful bead that they found, the number 6. Okay, number 6 and number 7. So okay, here is a little bit lower, but it's still the two best values that we reached were that two values. So the idea here is, okay, the software based on standard deviation follow the same trend that the weld engineer thinks that's a sound weld. Here for small detailed values, here's for austenity. Austenity presented a very uniformity weld bead over the voltage. We couldn't see much difference, both when you analyze the bead width, the reinforcement, and the, let's say, overall feature of the weld bead. But for the duplex, yes, again, it correlated with the index that we have been proposed. So here, with 16 volts, right? Yep. 16, 17 volts. We see the most, the bead that both weld engineers and both software thinks that the best weld bead. And the best weld bead was reached by the most stable process, with the one that was provided, the one that was carried out with the highest metal transfer regularity. So for stainless steel, for austenity, heading back, sorry, there's no this trend, but for ferricity we clearly see, okay, this is the best weld, best weld, best weld, and best weld. All of those best weld are the same. Be back, here, with the lowest value of the index that we proposed. As influence of the wire feed speed and the shielding gases, there's no too scattering to say something about that, because we vary too much the voltage, too much the current, so everything got mixed up. But okay, depends on the wire. You say, okay, for normally people try to study more austenitic stainless steel. They normally say, okay, please use 2% CO2, that you have a more uniformity bead, a better wettability. So here, okay, perhaps for austenitic we see we are in agreement with literature, but for duplex stainless steel, no, because the lower, let's say the best feature of the weld bead was achieved by using argon 2% O2. We still have to analyze again the metallurgy here, if everything changed, but you know, it's tricky because we have pure austenitic, you change the surface tension, you change a lot of things. Here's still a lot of work to carry out to clear all those aspects. So by this work we can conclude that yes, it's possible to weld within 15-19 volts. That's ordinary range for that steels and parameters that we have used. Austenitic wire present a stable condition over the whole range of voltage, and therefore both index curves and the position efficiency and the bead profile was kept constant. For the duplex wire, we saw a parabolic curve with a minimum of good regularity and a maximum of bead feature, let's say a beautiful weld bead, where minimum point indicates voltage levels around 16-17 volts for the wire we have used that led to best metal transfer regularity. And it correlates with both bead feature and the position curves. Correlation between the software that we developed, we call QBead, but it's just a name. So the software that we developed correlated with the grades or the scores that weld engineers they provide, and then therefore they could confirm the software that we did as a very useful tool to assess, okay, what we call that's a nice bead from the weld engineer's point of view. Again, we don't talk really about nice weld beads. We talk about qualified weld beads and non-qualified weld beads. But for a aesthetic point of view, we have a more uniform weld bead with a lower variation of its width or reinforcement. We can see a trend for duplex stainless steel that the more stable the metal transfer is, the more uniform the bead feature, geometrical features are. Okay, so thank you very much for your time.